You were taught that math builds on itself. First numbers, then algebra, then functions, then graphs. And for most people, that worked fine. The formulas made sense. The rules were followable. You could see the logic. Then, differential calculus arrived, and something shifted. Students who had been solid at math, students who understood algebra, who could read a graph, who passed every test before this one, suddenly felt lost. Not confused about one concept. Lost at the level of not knowing what they were even supposed to be doing. That is not a coincidence. And it is not because those students weren't smart enough. It's because nobody explained what differential calculus actually is before handing them a list of rules to memorize. By the end of this video, that changes. You will understand exactly what differential calculus does, why it exists, and how it works. No derivative rules yet, no memorization, just the real idea, explained clearly from the beginning. Here is the one sentence that explains all of differential calculus. Differential calculus is the math of measuring exactly how fast something changes at any given moment. That's it. Everything in differential calculus comes from two questions. First, what is actually happening at one specific instant in time? Second, how do we make that measurable when standard math wasn't built for it? Those two questions are what built this entire field. Keep them in mind. Everything that follows is the answer. Now, here's why any of this matters to you. Almost everything in the real world doesn't just change. It changes at a changing rate. Regular algebra handles steady, fixed situations cleanly. If you drive at a constant 60 miles per hour for 2 hours, algebra tells you the distance, 120 miles. Simple. If your salary is fixed and you want to know your annual income, algebra handles it. If a tank fills at a constant rate, algebra gives you the time. But what if the rate itself kept changing? A car that accelerates on the highway, brakes in traffic, slows for a curve, then speeds up again. A fever that rises slowly through the morning, spikes in the afternoon, then begins to fall. A stock price shifting every second based on thousands of simultaneous inputs. In every one of those situations, algebra can give you an average. It can tell you roughly what happened over a stretch of time, but it cannot tell you what is happening right now, at this exact moment, with precision. That is the gap, and differential calculus was built to close it. Before we get into the main tools, you need to understand one idea that makes all of differential calculus possible. It's called a limit. Here's what a limit means. A limit is the value that something approaches as you get infinitely close to a specific point. This matters because differential calculus constantly runs into a particular problem. There are moments where you cannot calculate the exact value at a point directly. The math breaks down if you try, but you can get closer and closer to that point, and as you do, the value you're approaching becomes clear. A limit gives you that value. It tells you what something is heading toward, even if you can never technically land on it. Here's an example. Open Google Maps and find a curved road. Zoom in on the curve. Keep zooming. The more you zoom in, the less the road looks like a curve. At a certain point, it looks almost straight. Zoom in further, and it looks completely straight. The road didn't change. Your perspective changed. The closer you looked, the simpler the shape became. A limit works the same way. You are asking, what does this approach as I get infinitely close? What does it look like when I zoom in forever? The key point is this. A limit is not about where something is. It is about where something is heading. That distinction sounds small. It is not. It is the entire foundation of differential calculus, and you will need it for everything that follows. Here's what the slope problem is. In algebra, slope is straightforward. You take 2 points on a straight line, you measure the rise, you measure the run, you divide them. That gives you the slope. It tells you how steep the line is and in which direction it's moving. This works perfectly as long as you are dealing with straight lines. But differential calculus begins the moment you ask a different question. What is the slope at a single point on a curve, not between 2 points? At one point, one exact location on a line that is constantly bending. This matters because the real world is full of curves, not straight lines. A population growing exponentially. A projectile following an arc. A temperature reading rising and falling across a day. None of these are straight lines. All of them have slopes that change at every single point. That is the problem differential calculus solves. The key point. Algebra can measure slope between 2 points, but it breaks down completely at a single point on a curve. Differential calculus was built specifically to handle that breakdown. Here's what rate of change means. It is how fast a quantity is shifting at one specific moment, not on average across an hour, not approximately over a stretch of time. Right now, at this instant, how fast is it moving? This matters because knowing the current rate tells you more than knowing the current value. Your phone shows 40% battery. That number alone tells you almost nothing useful. Is that 40% going to last 2 hours or 15 minutes? The percentage doesn't tell you. What tells you is the rate at which the battery is draining right now. If it's dropping 2% per minute, you have 20 minutes. If it's dropping 0.3% per minute, you have over 2 hours. Same battery level, completely different situation. The difference is entirely in the rate of change at that moment. That rate, measured at this exact instant, is precisely what differential calculus is designed to capture. The key point, rate of change is always about about one specific instant. Not an average, not an estimate, not a range. The exact rate, right now. Here's what a derivative is. A derivative is the mathematical tool that calculates the exact rate of change at any point on a function. This matters because once you have a derivative, you can find out how fast something is changing at any moment you choose. Not approximately, not on average, exactly. Imagine you have dashcam footage of a long car trip. You pause the footage at exactly 2:17 p.m. The car is mid-motion, clearly moving. What is its exact speed at that frozen frame? Not its average speed for the whole trip. Not its speed at 2:16 or 2:18. Its exact speed at that single frozen instant. A derivative calculates that. It takes a function, a mathematical description of how something changes over time, and gives you the exact rate of change at any point you choose to examine. Here is the part that surprises most people. The derivative is not a single number. It is a new function. When you take the derivative of a function, you produce an entirely new function that tells you the rate of change at every moment, not just one. So if the original function describes your car's position over the course of the trip, the derivative gives you a new function that describes your car's exact speed at every single moment of that trip. The key point, the derivative transforms the question of how is this changing overall into how fast is this changing right now, at this exact moment, and it answers that question not once, but for every point simultaneously. Here's what differentiation means. Differentiation is the process of finding the derivative. It is the actual procedure, the step-by-step method that you apply to a function in order to extract its rate of change information. This matters because understanding differentiation as a process, not just a result, is what allows you to apply it to any function in any context. The derivative is what you are looking for. Differentiation is how you find it. Imagine you are tracking how a virus spreads through a city over a period of weeks. You have a function that describes the total number of infected people on any given day. That function tells you the cumulative count, but what you actually need to know, what doctors and officials need to act on, is how fast the infection is growing right now. Is it accelerating? Is it slowing down? Is it peaking? Differentiation is the process of working through that total count function, step by step, to produce a new function, one that tells you the rate of growth on any day you choose. The original function told you the total. The derivative, found through differentiation, tells you the daily momentum, fast or slow, rising or falling, peaking or declining. The key point, differentiation is not a magic operation. It is a structured, repeatable process for extracting rate of change information from any function. The rules you eventually learn are shortcuts for that process. They are not the process itself. Now let's look at how these ideas fit together as one system. It starts with limits. Without limits, the slope problem has no solution. The moment you try to measure slope at a single point on a curve, you run into a situation where standard calculation breaks down. The only way through it is to ask what the measurement approaches as the two reference points get infinitely close together. That is a limit question. Limits are not a side concept in differential calculus. They are the ground floor. Everything else is built on them. Once you have limits, you can define the derivative. The derivative is what you get when you apply a limit to the slope problem and push it to its logical conclusion. It answers the question, how fast is this changing? Right now, at this exact point. Differentiation is the process of finding that derivative for any function you are given. It is the method. The derivative is the result. 3 mistakes appear consistently among students encountering differential calculus for the first time. The first is treating the derivative as an extension of the algebra slope formula. Rise over run works between 2 distinct points. The derivative works at a single point. These are not the same operation with different inputs. The derivative is only possible because of the limit. The second is learning differentiation rules as isolated procedures. The power rule, the product rule, the chain rule. These are introduced early and students begin applying them quickly, which can feel like progress. Third is stopping at the derivative without interpreting it. A positive derivative means the original function is rising at that point. A negative derivative means it is falling. The correction for all 3 is the same. Return to the question the derivative answers. How fast is this changing at this exact point, and in which direction? Every rule, every step, every sign in differential calculus exists to answer that question. Keeping that question present makes the rest of the subject readable.